Hey, welcome back. This is now 6.2, the law of cosines. We want to continue on solving oblique triangles. In particular, we need to know how to get to the side-side-side and side-angle-side variations, okay? Okay, so let's just dive right in there and start working with the derivation again. So the formula is kind of like a little weird. They're kind of like Pythagorean formulas. So recall, I guess, when you had the right triangle and you had three sides, you know, A, B, and C, you could say A squared plus B squared equals C squared. So maybe you kind of wonder, is there a similar variation for oblique triangles? Okay, so recall this thing, and it turns out there sort of is in a weird sort of way. So now for oblique triangles, we have basically, and I mean these would still work for the right triangles, but you could use them with the oblique. Okay, so again, kind of our picture. We have A, B, big C, and then little c, little a, and little b. It'll turn out that a squared is equal to b squared plus c squared. So you kind of see it's kind of like a Pythagorean. But then you have to go minus 2bc cosine of theta. Or sorry, cosine of angle A. Then there's two other versions. You could use b on the left. So b squared would equal a squared plus c squared minus 2ac cosine of big B. And then little c squared equals a squared plus b squared, which is most like the Pythagorean theorem, right? Minus 2ac cosine of c. And note, if we go over to our right triangle picture, and we kind of, you know, this would have been angle C. This would be, I guess, kind of weird. This would be angle B because the B is opposite. And then this would be angle A. But the point being that if you put, if we use the law of cosines formula on this right triangle, you would get c squared equals a squared plus b squared minus 2ac times the cosine of c. What is the cosine of c? Well, the cosine of c will end up being 0 because c is a 90-degree angle and the cosine of 90 degrees is 0. So you end up with c squared equals a squared plus b squared. Okay, so kind of it's like almost, if you know the Pythagorean formula, a squared plus b squared is c squared, you kind of already know these other formulas. You just have to tack on this weird, this other term, right? Okay, so hopefully, you know, remembering these formulas isn't too far of a bridge to cross. I don't know. We'll see how I want to do that on the test. But for now, let's go through and see if we could solve the other variations of the oblique triangle. So I'll leave the actual construction of these formulas to the book. You can read about it in the book, but I'm not going to spend time during this video to go through it. Let's just dive in to solving these triangles that we couldn't solve before. Okay, so section 2, solving oblique triangles again. Oblique, let me just put the triangle symbol. In the particular, we want now SAS and SSS. Okay, so for SAS, there's kind of more of an ordering than there was before, and you have to be sensitive to to the lengths of the sides of the triangle that you're working with. Okay, so first you're going to use the law of cosines to get the third side. Okay. And then secondly, you're going to use the law of sines to get the angle opposite the shorter of the given size. And I believe the reason why it's because you're going to have to use the inverse sine to do it, and you want to make sure you're working with an acute angle. And in either triangle case, if you think about oblique triangles, the opposite angle of one of the short sides, it's going to have to be at an acute angle. So you don't have that issue where you're taking sine inverse and you end up with two angles like we did in the previous section. Okay, so if you follow this, you don't have to worry about that issue. I believe that's the reasoning. I haven't really thought it through, but it seems to make sense. Okay, so use the law of sines to get the angle opposite the shorter of the given sides. Then thirdly, use the old a plus b plus c equals 180 degrees formula to get the last angle. Okay, so let's try a problem from the book this time. Let's try just number one. Let's see what they do. They're giving us an oblique triangle. Set up as usual, ABC, counterclockwise. This angle is 46 degrees. This side is 4. This side is 8. And this is just side A. So it is definitely side angle side. So we'll go with the program. First I'm going to find A. So A squared is b squared plus c squared minus 2bc cosine of A. Right? So A, we don't know. So A squared, B is 4, so b squared is 16, plus c is 8, so 8 squared is 64, minus 2 times 4 times 8, which would be 64, cosine of A, which is 46. So I'm just plugging and chugging. This will be A equals the square root of all that mess. We can simplify a little bit. Right? This will be 80. And then minus 64 cosine of 46. Okay? And if you put that all into your calculator, you end up with approximately 6.0. So I did that. Secondly, then, I want to get the angle opposite the shorter side. So there's two sides here, 4 and 8. So I want to get angle B. Okay. So first used the fact that you have little a and big A, and we're using the law of sines now. And then on the other side, little b, and we're trying to solve for big B. Okay. Okay. So isolating sine of B, you'll end up having sine of B equaling 4 sine 46 all over 6. And then taking inverse sine on both sides, B will equal sine inverse of that. 4 sine 46 all over 6. And you put that in your calculator. To the nearest degree possible will be 29 degrees. And you don't have to worry about the other because you know, in this case, you know that it has to be an acute angle. B has to be acute because A and the side you're across from is the shortest side. So it has to be the shortest interior, or one of the two smallest interior angles. And when you're dealing with obtuse triangles, the only possibility is you have one obtuse and two acute, or you have three acute. So there's just no other way to slice it. If you're across from the one of the two shorter, so I mean, either this is the shortest side, 4 is the shortest side, or it's one of the two shorter sides. In either case, it will have to be across from one of the acute angles. The only possible obtuse angle would be angle C. Okay. So there's none of this, you know, take 180 minus 29, and that's a possibility for your other angle. Okay, you don't have to worry about that like you did in 6-1. Okay, so I think I beat that to death. Step 3 then is just to solve out for your third unknown angle, in this case C. So C will equal 180 minus, one of them is 29, the other one's 46. And that'll equal 105 degrees, and you're done. Okay, let's move on to side-side-side problems. Part B. If you read the book, they have an interesting problem on what is that thing about? It's like something about dinosaurs or something. Paleontologists study dinosaur foot tracks, and they need to know the angle inside these foot tracks for some reason. And I guess they can use this process to determine that. So you have all three sides of an oblique triangle. The process, again, you have to take into consideration the length of the sides of the triangle. So first you're going to use the law of cosines to find the angle opposite the long side. Then secondly, you're going to use the law of sines to find the other angles, because those will be acute angles. Okay, so use law of sines to find angles opposite the other angles. Find angles. Use the law of sines to find the other angles. Sorry. And of course, you'll find 1, 2, and then just use the ABC formula to find the third. Okay. Let's look at some problems from the book then. Number 8. Okay, so they give us this oblique triangle. A, B, C. This is little b is 16, little a is 10, and little c is 8. And so, work with the angle opposite the longest side. So in this case, that'll be angle B. So I have b squared is equal to a squared plus c squared minus 2ac cosine of big B. Okay, fill in the unknowns. 16 squared, whatever the heck that is, 16 squared equals a squared, which is 100. 10 squared is 100. And then plus 64 minus 80 times 2 is 160. Cosine of angle B, which I don't know. Okay, so this will be 164. Move it to the other side, so you have 16 squared minus 164. I'm going to figure that out. Gosh, 16 squared minus 164 is 92. And then you have negative 160 cosine of B. Divide both sides by negative 160, so you'll have cosine of B equals negative 92 over 160, and then take cosine inverse on both sides. It should give you an answer. Let me look. So, negative 92 times 160 is, I'm getting 125.1-ish. So to the nearest degree, it's 125 degrees. Okay, then you use law of sines to get the next angle. So I need to kind of see my picture a little bit. So step 2, I'm going to use law of sines. And I have the, what do I have? It looks like I have B. Do I have little b? Yeah, of course. So little b is 16 all over sine of 125. And on the other side, just to be consistent with my notes, let me see what I did first. First, are you forced to actually do something? You know, we have one angle, basically the 125 here, No, we're not really forced. So we could do either A or B or C. A or C. Let's do A, just going in alphabetical order. Even though it looks like in my notes I did something else. So, no, we'll go with A. So little a is 10, and then all over sine of angle A. So solve for sine of A. Sine of A is equal to 10 sine of apparently 125 all over 16. So A is sine inverse of that. And plop that into your calculator. Sine inverse 10 sine 125 all over 16 is going to be, to the nearest degree, it looks like it's 31 degrees. Okay, and then you could just use the, the 180 formula. C equals 180 minus 125 minus 31. 180 minus 125 minus 31 is 24 degrees for your final angle. Okay, let's look at one more of those just to be sure we're all on the same page. Let's look at number 18. This time they just give you the information. They don't give you a picture or anything. A is 4, B is 6, and C is 9. So step one, you're going after the angle opposite the longest side, right? So we're going C squared equals A squared plus B squared minus 2AB cosine of angle C. So C squared, it'll be 81. That'll equal 16 plus 36 minus, looks like 70. 24 times 2 is 48 cosine of C, I believe. And then I'm going to solve for cosine C. So 81 equals 52 minus 48 cosine of C. So I'll have 81 minus 52. 8, 9, 2, 29 equals negative 48 cosine of C. And then divide both sides by negative 48. So cosine of C equals negative 29 all over 48. Do cosine inverse on both sides. So C equals cosine inverse of negative 29 all over 48. And then finally get an approximation to the nearest decimal, or the nearest degree, excuse me. So cosine inverse of negative 29 divided by 48 is apparently 127 degrees. Okay. Then you go to your sine, law of sines. So we have little c, which is 9 all over sine of 127. And on the other side, I know, just going in alphabetical order, I guess we'll go for big B, right? So 6 all over sine of big B. Okay, so solve for sine of big B. That'll be 6 sine of 127 all over 9. So big B will be sine inverse of 6 sine 127 over 9. Let's get that quickly. So sine inverse 6 sine 127 over 9 is 32 degrees apparently. And then finally get angle A using 180 formula. 180 equal minus, A equals 180 minus 32 minus 127 is apparently 21 degrees. Okay, so that solves that issue. Let's take a look at a application, and then there's one extra formula we want to introduce. So I'm going to look at example 3 on page, I believe it's 727. Okay. Excuse me. Where are you? Okay, so two airplanes leave an airport at the same time on different runways. One flies at a bearing of north 66 degrees west at 325 miles per hour. The other guy is flying, or gal, at south 26 degrees west at 300 miles per hour. How far apart are the airplanes after 2 hours? Okay. So let's draw a picture. And if you remember the work with bearings from a previous section, this is north, this is south, this is east coast, this is west, and you're kind of going down from the north or south in the direction west or east. So for north 66 west, you start at the north and then you dip down to the west by 66 degrees. Okay, so you're going to end up with this, and that's the trajectory of one of the airplanes. Okay. Then south 26 west, so I start at south and then dip down in the direction of west by 26 degrees. Okay. And we kind of have an oblique triangle. We kind of need to know the distances on those two sides. Ultimately, we want to know that distance that I just drew, which is the distance between the two planes, right? How far apart are the planes after 2 hours? Okay, so I can use a little bit of just geometry to figure out this angle here. Okay, so that's going to be, because the entire, let me draw another angle. This angle here is 180 degrees. I can figure out the red angle by just taking 180, let me draw on black, 180 minus the 66 minus the 26. Okay? So it'd be 180 minus 92, which would be 88 degrees. Okay, so this is 88. I can get the sides of these two, let me put it in yellow, which sides I'm talking about. So yellow, I need the distance of that side and the distance of that side, and then I'll have a side angle, side triangle, and I could solve that for this opposite side over here. Okay. So the yellow ones you can figure out because the plane was traveling for 2 hours at 325 miles per hour. So that's this information, plus the formula distance equals rate times time, right? So for the first plane, let's call it D1, D sub 1, that'll be rate 325 miles per hour times 2 hours. Okay, so that's 650 miles for that side. D2 will be 300 times 2, which is just 600. That'll be this side. Okay. Okay. So then we can, we need this third side. So can we get it just using the law of cosines without having to literally solve for everything? Let's label up the sides first. So let's call this guy A, this guy B, this guy C, and then we have what is this? Little b, and then we know little c and little a. Okay. So is there any formula? So we want a formula that's going to be for b. So b squared equals a squared, which we know, plus b plus c squared, which we also will know, minus 2ac times cosine of big B, which, yeah, so we're going to be able to solve for b pretty easily. Okay, so b squared will be a squared, which is 650 squared, plus c squared, which is 600 squared, minus 2 times the product of those two, times cosine of 88 degrees. And then you just take the square root of that thing. And I'll do that in my calculator, so I don't have to be burdened by rewriting that. Okay, so let's see, second square root, 650 squared plus 600 squared minus 2 times 650 times 600 times cosine 88. I'm missing a parentheses. Okay, so it looks like I'm getting 869 rounded to the nearest mile, 869 miles. Okay, this actually comes up in real life scenarios, believe it or not, and you may want to let me if you want to pause the video here, you can. I'm going to show you an example. It may be kind of traumatic for some people. It may be kind of a trigger. So if you don't want to see this, you can pause the video, but it's about an airplane accident. Okay, so if you need to pause the video and stop, you can go ahead and do that. Well, hold on. Let me give you the last example, and then so you can just stop and not have to watch. Let me also tell you which problem was the video quiz, which I apparently decided to skip again. So the video quiz, I'm going to find it. The video quiz is supposed to be number 18. Okay, so this is actually the video quiz for this section. So if you want to, you can just stop the video now and not have to worry about anything. In other words, I'm going to look at an example on airplane crashes starting right now. So yeah, so hopefully you just stop the video if you don't want to watch it. Okay, so this is on an airplane crash. I think it was in the 70s around the Vietnam War, and it was a Phantom jet. I think it was called an F2. Is that what a Phantom is? F2 Phantom crash with a DC. I think maybe it was a 10, maybe a DC 10. It must be this one. Okay. So back in the day, military aircraft and the civilian aircraft weren't on the same kind of air traffic controlling systems. So you could have these military jets flying around, and the civilian jets didn't even know they're in the area, right? So the deal is, that's exactly what happened. I think it was a Navy jet. The Navy jet ended up having to get some repairs done, and then on its way to the base to get the repairs done, it collided with a civilian aircraft. And this is the report about it. So in particular, one of the issues was whether or not the two planes could actually see each other, right? Because they're going at such a high rate of speed that it's possible that, you know, as you're looking far away, and this is what you're seeing on the web page here is the cockpit view for the DC-9. You're looking; these are little windows. These are basically the windows of the DC-9. As you're out looking out the window, the Phantom jet could be in between the two windows, right? It could be sitting there, and then when it finally, I guess I'm done with my office hours. Then when you finally see it, like right here, and you could see the F4's calculated path. When you finally see it, it could be too late, right? Or maybe it was farther away here. This is 80 seconds prior to their impact. And at that time, it was just a little dot. And then when it's like 20 seconds to impact, it's in between these two windows, and they couldn't even see it, right? So in order to kind of figure this all out, they had to diagram the two planes. So you can imagine down here at this point would be the DC, I guess it's a DC-9. I'm not like a airplane buff or anything, but then the plane up here is then the phantom jet. And what they're doing is calculating distances and speeds between these two points as they go towards the collision point. And they're trying to see how fast they were going and whether or not that was the case where they just completely did not see each other, right? So, we're wondering, is this just because of the way the windows are, that's why they ended up hitting each other, or is it because of some pilot error? Maybe the pilot wasn't even looking around in the space, he was just kind of chilling at that moment. So guess what equation then they used in order to kind of fill out this triangle? Well, law of cosines. It's literally an application of what we learned here in class today. Okay, so I mean, I always thought these transportation reports were kind of way too technical for the average civilian humanoid to read, but that's not true. If this is something you're interested in, you could go online and look at these reports, and they turn out, so long as you know a little bit about airplanes and that sort of thing, you can read the report, and they oftentimes have mathematics in the report, and if you take enough math, you'll be able to understand the math, which is kind of cool, right? So a gory example, I think everybody died except maybe one of the pilots, the Phantom Jet. I saw it originally on TV, and then I was wondering, could I, like you probably would wonder, could I actually read the report that they made? And I read the report, and I was just thrilled to see that the math lines up with the math that I teach down here with the law of cosines. Okay, so kind of a gory example, but if that's the kind of thing you're interested in, clearly, yeah. Somebody told me that air traffic controllers use a lot of math in their job, or at least that maybe they're making a lot of mental calculations, which is probably a very good, solid job to have. But I think it's extremely stressful, and you have to be a pretty straight edge fella to do that kind of job. But anyways, there's that. I just wanted to show you an application, something that was a bit more interesting than what we usually see with the dinosaur application. Was kind of interesting in the book. But okay, so thank you for watching, and we will see you next time.